Hello everyone, my name is Alexander Fedotov. I am a PhD student from Eindhoven University of Technology. In this presentation I will talk about effective system-level liveness verification of hardware designs. Let me start with a quick overview of our work. The work is done in the context of XMAS. This is a language that was originally introduced by Intel for describing hardware designs. XMAS is a graphical language, so one can easily build high-level models by composing primitives. Originally there were 8 core primitives. An important question is whether an XMAS network is live, that is, whether data cannot get stuck in the network. For core XMAS, efficient liveness verification techniques were introduced by Gutmanov and others. Some time ago, Verbeek and others extended XMAS with finite state machines. They also extended liveness verification to support finite state machines. The addition of FSMS to XMAS increases the expressivity of the language and enables, for instance, the verification of liveness of on-chip cache coherence protocols. Unfortunately, as we show in this presentation, the liveness analysis proposed by Verbeek and others is unsound. Later in the presentation, we will illustrate this with a counterexample. In our work, we propose an alternative liveness verification technique for XMAS with FSMS and prove that it is sound. To have an intuition about XMAS networks, let us first consider a simple example. Here, we have a source that produces a datum and passes it to a fork. The fork receives the datum, duplicates it to both outputs and passes it on to a pair of queues. Now, the topmost queue cannot yet forward the datum to its output, since the join requires data to be available on both inputs in order to proceed. Therefore, the bottom queue must first pass the datum to the empty queue. Now, both queues connected to the join contain data, and they both simultaneously provide their data to the join, which accepts the input and passes a single datum further to its output, where it is finally accepted by the sink. If we zoom into a single connection in XMAS, two primitives A and B are connected by a channel X. Suppose A wants to transmit data to B, then we call A the initiator and B the target of the channel. If we zoom in further, we see that channel X consists of 3 signals: iReady, tReady and data. These signals are used to encode a handshake protocol. iReady indicates that initiator is ready to send data. Data contains the data that is transmitted from initiator to target, and tReady signals that the target is ready to receive data. Data is only transferred if both iReady and tReady are true. The main verification in an XMAS network is to decide whether it is live. Intuitively, this means that whenever a primitive in the network is ready to transfer datum D along channel X, eventually the corresponding target is ready to receive that datum. We use the illustration of channel X to make this notion of liveness more precise using LTL. We say channel X is idle for datum D when at some point the initiator of channel X does not attempt to transfer D anymore. Channel X is blocked for D when at some point the target of channel X cannot accept D anymore. We say that channel X is live for datum D when either it is idle for D or it is not blocked for this D, or, viewed as an implication, whenever channel X is not idle for D, it is also not blocked for D. If a network is not live, there is a path in the network that satisfies its negation, which is characterized as dead. So, a channel is dead for D if, at some point, the initiator is ready to transfer D, but the target is never able to accept it. The key liveness verification technique associated with XMAS networks generates a SAT problem that approximates the idle and block properties. The SAT encoding is such that from a path that satisfies dead, a satisfying assignment can be constructed, so the approach is sound. Let me illustrate the SAT encoding by Gutmanov and others using an example. Here We have an XMAS network that consists of a source, a queue, and a sink, and two channels X and Y. For the sake of simplicity, we only have one datum, the token T. We approximate the LTL formulas for idle and block as follows. Channel X is the output of the source. Sources produce data infinitely often, hence channel X is not idle. Channel X is the input of the queue. The input of the queue is blocked when the queue is full and the output of the queue is blocked. Channel Y is the output of the queue. The output of the queue is idle when the queue is empty and the input of the queue is idle. Channel Y is the input of the sink. Sinks in XMAS consume data infinitely often, thus channel Y is not blocked. Note that any assignment consistent with the equations must also conclude that X is not blocked and Y is not idle. Therefore, we conclude that both channels X and Y are live. In 2016, Verbeek and others introduced finite state machines into XMAS to make the language more expressive. An FSM in XMAS has inputs and outputs, a finite number of states, and one initial state. Every state has at least one outgoing transition. Along every transition, the FSM reads a datum from exactly one input channel, which is indicated using a question mark, and writes a datum to exactly one output channel, which is indicated using an exclamation mark. A transition can only be taken if the input channel is ready to provide the datum specified by the transition and the output channel is ready to accept the datum output by the transition. In the example on this slide, the XMAS network contains a finite state machine with two input channels X and Y and two output channels O and Z. Both inputs are connected to sources and the outputs to sinks. For simplicity, we again assume the data consists of a single token. We therefore do not specify it explicitly in the example. I illustrate a part of an execution of this XMAS network. Initially, the FSM is in state as 0. When the source connected to channel Y is ready to produce a token and the sink connected to channel Z is ready to accept a token, the transition from S0 to S1 becomes enabled, which makes the T-ready signal of channel Y and the I-ready signal of channel Z true. The FSM takes the transition from S0 to S1, consuming the token on Y and producing the token on Z. Once the FSM is in state S1, it can never read from channel Y anymore, and the T-ready signal of channel Y will remain false forever. Since Y is connected to a source, its I-ready signal will eventually become true and channel Y is dead. Okay, let's hold on to that though, and see how the approach by Verbeek and others detects this dead channel. Verbeek approximates the LTL formulas for idle and block in FSMs using the following SAT equations. An input channel X of an FSM is blocked for some datum D if and only if either the FSM is dead or there is no transition in the FSM that reads D from X. Likewise, an output channel Y is idle for datum E if and only if either the FSM is dead or there is no transition in the FSM that writes E to Y. A finite state machine is dead if and only if one of its states is dead, which means that that state is current and all of its outgoing transitions are dead. A transition from S to S' that reads D from X and writes E to Y is dead if and only if either X is idle for D or Y is blocked for E. Here, the intuition is as follows. A dead FSM is supposed to eventually lose the ability to read from its inputs and write to its outputs. The authors suppose that it happens when the FSM reaches a state which cannot be left, since all the outgoing transitions from this state cannot be taken. So, at the first glance, this encoding seems reasonable. However, As we will see, this encoding does not detect the dead channel from the previous slide. So, reconsider the XMAS network with a finite state machine that we saw before. We show the encoding by Verbeek. Since channels X and Y are connected to the sources, the channels are not idle. Since channels O and Z are connected to the sinks, the channels are not blocked. Assume that the FSM is currently in state S1. According to the equations, the self-loop on S0 is dead if and only if X is idle or O is blocked. The transition from S0 to S1 is dead if and only if either Y is idle or Z is blocked. And the transition from S1 to S1 is dead if and only if either X is idle or Z is blocked. Hence, none of the transitions is dead. State S0 is dead if and only if it is current and both its outgoing transitions are dead. State S1 is dead if and only if it is current and the transition from S1 to S1 is dead. The FSM is dead if and only if either S0 or S1 is dead. Since none of the transitions are dead, S0, S1 and the FSM are not dead. Since channels X and Y are only blocked if the FSM is dead and channels O and Z are only idle if the FSM is dead, we conclude that X and Y are not blocked and O and Z are not idle. This is clearly incorrect since, as we previously observed, when the FSM is in state S1, it can never read from Y and Y is therefore blocked. If we look more closely at the encoding, it incorrectly observes that all the transitions are live, but in fact there is a state that eventually becomes unreachable and as a consequence some transitions cannot be taken anymore. We therefore propose the following alternative encoding. Given an input channel X of an FSM and some datum D, we say that X is blocked for D if and only if all the transitions in the FSM which involve reading D from X are dead. Similarly, given an output channel Y and some datum E, Y is idle for E if and only if all the transitions that involve writing E to Y are dead. The intuition is that a dead transition eventually cannot be taken anymore. A transition from S to S' that reads D from X and writes E to Y is therefore dead if and only if either its source state S is idle, input channel X is idle for D, or output channel Y is blocked for E. Essentially, a transition can eventually not be taken anymore if either its source state S eventually becomes unreachable, the environment can never write D to X, or it can never read E from Y. Idle S encodes that S eventually becomes unreachable. This is the case if it is not the current state and eventually none of its incoming transitions can be taken. Let me use the counterexample from the previous slide to show that our encoding correctly detects that channel Y is dead. We again show the equations on the right-hand side. Recall that since channels X and Y are connected to the sources, the channels are not idle. Since channels O and Z are connected to the sinks, the channels are not blocked. Also assume that the FSM is currently in state S1. The self-loop on S0 is dead if and only if either S0 is idle or channel X is idle or O is blocked. The transition from S0 to S1 is dead if and only if either S0 is idle or Y is idle or Z is blocked. The transition from S1 to S1 is dead if and only if either S1 is idle or X is idle or Z is blocked. State S0 is idle if and only if either it is not current or the self-loop on S0 is dead. State S1 is idle if and only if it is not current and both its incoming transitions are dead. We see that setting S0 to idle, the self-loop on S0 and the transition from S0 to S1 to dead gives a consistent assignment for each of their defining equations, since S0 is not current. Since S1 is current, S1 cannot be idle, and therefore the self-loop on S1 cannot be dead. We conclude that channel X is not blocked, but channel Y is. Also, channel O is idle, whereas channel Z is not. Therefore, we correctly conclude that channel Y is not blocked, and since the environment ensures it is not idle, channel Y is dead. More generally, we can prove that our encoding is sound in the following sense. If there exists a fair maximal path in the XMAS network that witnesses that channel X is dead for D, then there is a consistent satisfying assignment for the SAT problem that contains all idle and block equations generated for the XMAS network, in which the variable denoting channel X is idle for D is false, and the variable denoting channel X is blocked for D is true. The proof of the theorem entails constructing a satisfying assignment from path pi. More details can be found in the paper. Note that the encoding by Gutmanov and others for core XMAS is already incomplete, so we do not worry about completeness here. To determine how the encoding performs on actual XMAS networks, we implemented it in a tool. Our tool converts a given XMAS network into the corresponding SAT problem, such that liveness of the given XMAS network can be verified using a SAT solver. In addition, our tool is able to generate an SMV model corresponding to the XMAS network, such that liveness can be verified using new XMV. We evaluated our implementation using two sets of models. The first is inspired by go-no-go testing. The models in this set are balanced binary trees of go-no-go blocks. Every block consists of two interconnected FSMs and has two binary inputs and one binary output. The output is OK if the data on both inputs is OK, and it is not OK otherwise. The second set is inspired by a real-world dynamic power management policy. The models in this set have a number of power domains, and each domain has a dedicated power controller. Every power domain has a number of device controller pairs. The domain power controller gives power to the domain when one of the devices indicates activity. The domain is powered off if all device controllers indicate that their devices are turned off. Multiple power domains are controlled by the top power controller. Each of the models has a corresponding version in which a deadlock was introduced artificially. We verified each model using both the SAT-based verification and the new XMV-based deadlock states reachability analysis. Both SAT and reachability correctly indicate absence or presence of deadlocks in all models. For both experimental sets, we generated instances with different numbers of finite state machines. We evaluated scalability using these models. The largest go-no-go models contain 126 FSMs. Liveness of the largest deadlock-free go-no-go model is proven using SAT in 7 seconds. Reachability analysis takes about 2 minutes for the same model. For the largest go-no-go model with a deadlock is reported using SAT in about 6 seconds. Its existence can be proven using reachability in about 4 minutes. For the power domains, the largest models, both with and without deadlock, contain 1,299 FSMs. For the largest model without a deadlock, SAT proves liveness in about 9 minutes. Analysis of the largest power domain model with a deadlock takes about 8 minutes. Reachability analysis for the power domain models with number of power domains larger than 30 was not possible since NuXMV exceeded the maximum allowed stack on the machine on which the experiments were performed. Here you see a visualization of the results. Note that we use logarithmic scale for the y-axis. If we look at the results, we see that both methods scale exponentially in the number of FSMs. However, using SAT for liveness verification significantly outperforms reachability. To conclude, we showed that the liveness analysis of XMAS networks with finite state machines by Verbeek and others is unsound by giving a counterexample. We presented an alternative encoding that incorporates reachability of states in an FSM in the satisfiability encoding and proved its soundness. We demonstrated using two classes of examples that our implementation using satisfiability outperforms symbolic reachability in new XMV. As I mentioned during the talk, approximating liveness of XMAS networks using satisfiability is not complete. Therefore, in practice, it is possible to get false deadlocks. Although in our experiments we did not observe such false deadlocks, it remains to be seen whether this is also the case in industrial case studies. Therefore, further experimentation is needed. If it turns out that many false deadlocks are generated, we need to investigate techniques that reduce the number of false deadlocks. One of the possible improvements to our method is to add invariants that reduce the number of unreachable deadlock states that are reported. The current notion of finite state machines in XMAS networks has as a drawback that it can only read from one channel and write to one channel on every transition. Allowing simultaneous reads and writes from and to multiple channels would not only allow for more concise implementation of some networks, it would in fact increase the expressivity of XMAS with finite state machines. This concludes my presentation. I would like to thank you for watching. The implementation of the tool is available on the GitHub page shown on the slide. The GitHub page also includes some documentation as well as the models used in the paper, with a detailed description. If you want to know more, have a look at the paper or reach out to us.